Okay, good morning, everyone. Welcome back to the Topos Colloquium. Today's Thursday, March 6th, and for those in most of North America, or at least the continental US, the Colloquium will move times next week with daylight savings time coming into effect. So be ready to possibly come an hour later. If you're on a different continent, or you just live on UTC because you're just as advanced as the Topos Colloquium, then you won't have to change anything for now. Today, we're very excited to welcome Matteo Capucci, a category theorist from Strathclyde, who is working along with many European category theorists this year on the ARIA Safeguarded AI program. He's been digging into double categorical systems theory, and that's what he's going to tell us about today. Matteo, take it away.
Hello, hi Kevin. Thank you for introducing me, and thanks for Topos. Thanks Topos for inviting me, and it's really nice. So the talk today is going to be, so first of all, we're going to have spoilers because you can see my slides appearing from the bottom, but it's going to be quite simple to some extent. Like as I say in the title, it's all the new wisdom, mostly old wisdom. So double categorical systems theory is this framework that coalesced in the last few years. Surely David Myers was instrumental in this and putting together like this interesting picture of modeling mathematically the ontology and phenomenology of systems using double categories. But surely there's a lot of ideas that came before that. First of all, we must mention algebraic automata theory, in which we have the probably most successful categorical frameworks to deal with systems at the level of like fame and number of results and literature. And it has this very important quality, which is it deals with systems as objects of a category. Which is something that's really put to good use using morphisms between the systems to say many interesting things. So that's one first idea. And then, of course, the very fertile line of work on systems as algebras for operands that's been very well developed, especially in that part of the US where this seminar is virtually in. So Topos, in which, so algebras for operands means that we have these drawings or these things that we use to compose systems, and then systems are things that we can use to we can compose with these things, right? And then there's a line of work on by categories for transition systems that certainly double categorical systems theory has taken some ideas from, in terms of working with two-dimensional structures to both combine the compositional and categorical aspects in the same picture. And finally, double categories of structure cospans, and generally speaking, double categories of open systems. That's something that John Baez, Kevin Corser, and many other people, including people at Topos, have worked on, and introduced the idea of double categories as a very good structure to deal with indeed composition and categorical structures at the same time. So just a really quick overview of what we're dealing with. So in double categorical systems theory, systems are algebras of symmetric double operands. But in this talk, we're going to be just dealing with symmetric monoidal double categories, which we think of composition operations, and they indeed compose the systems. And so we can think of these systems as little, I need a pointer, as this kind of, oh God, at this kind of little modules, which is something that David Jess and other people are exploring very thoroughly at the moment. And then on top of that, we can talk about functors between this, right? And so specifically, we'll see behavior as a functor, or better, a map of this algebras of double operads that therefore is going to account for both the categorical or morphological aspects of systems, which are going to be mapped functorially, but also taking care of the compositional aspects, being a morphism of algebras of some kind, right? And so in this talk, I'm just going to talk about these two things. So first, I'm going to tell you this idea of seeing systems theories as modules or composition theories, and give you some examples just to ground the intuition. And then I'm going to dive into the core of the talk with representable behavior. So I'm going to say what behavior is, how to obtain it using indeed representables. And then most of the talk is going to be about compositionality theorems, especially in the extended case of multi-employer representable behavior. And I got to say, like, there's literature, there's references here. So some things are not due to me originally. There's a big book by David Jazz on this stuff that I mentioned before. There's other papers. So I'm not claiming originality in 100% thing, but there's definitely original stuff here. Just didn't want to annoy anyone. So conventions. So this is going to be about double categories. So to me, double categories is always weak. Double functors always lax. I usually follow Grandis conventions for double categories. And then the other big double convention that I follow, which is not Grandis, is that I don't distinguish in horizontal and vertical arrows. I distinguish between loose and tight. So the loose arrows are always drawn with a mark, usually the dot, sometimes the little med symbol for profunctors. And then, yeah, I usually say arrows for the loose arrows and morphisms for the time morphisms, because I consider them to be very different things. But anyway, let's dive in. So theories of compositions and theories of systems. A theory of composition is a really simple thing. Now, there's a bunch of adjectives in front of double operad, but the core of the definition is double operad. So a double operad is an operad in categories. So an operad has a bunch of colors and these operations with arity. And here is the same idea, except the colors form a category. And so they have maps between them. And then the operations also form a category and they have maps between them. But most importantly, a theory of composition has an attitude, which means a way to conceive and think about those that is some sort of informal mathematical meaning that we attach to it in this line of work. And this is the idea that a symmetric double operad is representing interfaces which have composition operations between them, right? And so if we have this like ports or in the interfaces in the broadest sense possible, and then you have a formal operation that tells you how things with a given interface can be all assembled together and expose a new interface, right? And then the horizontal direction here, the type morphisms are maps between these interfaces, whatever this means, and the squares are maps of composition, right? And so, as I said before, we actually just consider this to be symmetric monoidal double categories, so representable symmetric double operads for the moment, because it's just easier. Like a biblically accurate version of this theory would go like dive straight down into double operads, but that's not the aim of the talk at the moment. And now for theories of systems. So a theory of system over a theory of composition I is given, first of all, by what I call the type datum. So the type datum is the specification of all the stuff in these theoretic systems. And by stuff, we mean two things. We mean systems, meant as objects in the category sys, and maps of systems, right? Which are the morphisms in this category. But then we also want these stuff to be organized in the following way. We want systems to be displayed over interfaces, specifically I0, so the category of interfaces that we get by forgetting all the double structure of I and just keeping interfaces and maps. And so each system is displayed over its interface. Each map of systems has corresponding map of interfaces between the interfaces of the systems we are mapping. And everything is symmetric monoidal in the sense that if we put together two systems, then they're going to be over the monoidal product of their interfaces, right? Without any, like strictly, so without any isomorphism in the middle. And this is the tie data. And then we have the algebraic part, which is given by the module structure on this data, right? The way we equip this display category with algebraic structure is by having the composition theory act on it. So the composition theory is a symmetric double category, symmetric monoidal double category. So in particular, it can be seen as a span in categories that we can use to act on this functor, this display category here, with a pull push operation. And then a module for this action is an algebra structure like this, which we just read is strong monoidal. It's also like symmetric monoidal functor. So the way we should think of this is, well, what this is actually taking a pair of a system and a composition operation out of the interface of said system, and it's composing them in some way. So given this as bullet P system. And of course, we have an analogous operation on morphisms, right? So we have a way to compare systems and a way to compare compositions, then we get a way to compare the composites, all right? And then, of course, this operation is unital associative as like any algebra of a monad. But since this is we are in categories, so this is actually a pseudo-algebra of a pseudo-monad. And so we have a structure morphism witnessing unitality. We have a structure morphism witnessing, let's say, associativity. And then I also added the interchanger that we get by assuming this is a strong monoidal functor. And I saved you from the coherence conditions, which are pretty standard. All right, so a theory system is a bunch of systems displayed over interfaces over which we can act with the operations of I. So let's see some examples. Well, the easiest example we have is the case of a finitely complete category E, to which we can associate spans in E as a double category, which we think of as a theory of composition, in which, well, the interfaces are like observation types, right? So something, imagine we can observe some things, we can measure some quantity, and these are values in E, right? So E can be set, mostly gonna be set, but it can be sets varying in time, it can be smooth sets, it can be logical spaces, you know, there can be more structure on these observations. And then an operation, composition operation, is but a way to basically put in communication two interfaces with a process that we know only by like what it does on interfaces. So given an observation here and an observation here, I'm going to have a type of things that could be happening in this process that A and B are compatible with, okay? So this is a relational way to conceive processes. And most importantly, we can also see as something that composes systems. So over this theory of composition, we consider the type data given by the codomain vibration, right? And this is just, indeed, the systems there are just display maps, and display maps can be, which are just maps in this case, can be pulled and pushed along this. And this corresponds to, we have a system with some observations, and then we can join them with whatever is happening in this process and get a new system with observations in B, which is like compatible with this composition thing. Okay. And we call this a behavioral theory because again, it corresponds to a behavioral view of systems in which we don't know anything dynamical about the system, we just know what we can observe about them.
Matteo,
Sorry.
that rotated semi-direct, I guess either slide is fine. That rotated semi-direct product symbol, you're just using that for a fiber product?
Yeah, good catch. I use this to denote pullback, but also sometimes like compositional spans. So it's a versatile symbol.
Yeah.
Okay.
Symbol. Thanks.
Oh, thanks for the question. Right, and let me stress that when E is a regular category, so we have an epimonofactorization system, then we can actually construct a category of relations, which is very similar in spirit, except these spans are now jointly monic, meaning that it's not like we're considering things that can happen given some observation at interfaces, we're just considering whether something can happen or not. So we're completely black boxing our systems and our processes. And we only remember if something can or cannot happen. So let me extend this example a bit by introducing adequate triples to our notion from this work, which I extended with the monoidal structure here. So an adequate triple is a category, in our case a monoidal category, equipped with two wise subcategories of morphisms, the ingressive and egressive ones, with the following axioms. So every iso is ingressive, both subcategories are closed under monoidal products, and this is the most important one. So every cospan like this can be completed to a square like this. So we can pull aggressive maps along ingressive maps, and we again get an aggressive map and an ingressive map. And then we want monoidal product to commute with these pullbacks, and so in this case we get a nice displayed symmetric monoidal category of aggressive maps over E. And from this, we can build, again, a double category of spans, symmetric monoidal double category, which works exactly in the same way as before, except now the spans are being restricted to be of this form, where the left map is ingressive and the right map is aggressive, okay? And given the axioms of adequate triple, then we can compose and pull-push aggressive maps in the way that we need. Now, the reason we do this is because we can treat on other examples similarly as the behavior theory introduced first by using this idea of adequate triples. And then, so say P is a strict symmetric monoidal vibration. So we can think of E as a category of P charts. So it's simply a way to represent E in which objects of E are notated over the object of B they're over, and the maps of E are factored as vertical and Cartesian parts. All right. And then it's straightforward to see that vertical and Cartesian maps are the ingressive, aggressive maps of an adequate triple over E. And therefore, we can define a double category of spans in this way. And such double category of spans is actually thin, because this map in the middle can always, like in the case of this example, not always for any adequate triple, can always be I mean, the commutativity forces it to be of this form. And thin means that there is at most one map, one square with a given boundary, of course. And now a span like above, so we're with a vertical Cartesian legs is also known as a p-lens and has this form in which like one map goes forward, one map goes backward. And so this can be used to model bidirectional processes in which the backward part is conceived as happening later than the forward part, and that's why it can depend on it, okay? And these were defined by Spivak in index form, and in this paper, we give an account, a vibrational account of the same stuff. And then, of course, for the codomain vibration set, these p-lenses are actually the category poly that is very famous at Topos, right? But of course, here we're considering like a double categorical version of polling, which we also have in this other direction of charts. Anyway, so this double category is now of this form, and it's called lens. And this is, again, this is a bidirectional process, and this square is witnessing this bidirectional process being mapped into this other bidirectional process. And basically the square, like, is witnessing two separate commutativity conditions, which are these ones. It's not super important that we go into this in detail right now. So over this theory composition, we can consider two theories of composition. So now we're focusing on the set case. So deterministic discrete Moore machines. So our Moore machines with state space is a set, and whose interface is indeed a polynomial functor or a bundle, depending how you think about this. And a Moore machine is then a lens like this, which amounts to this maps like this. So this is called a view or observation map, and this is called an update map. And then a map of these Moore machines is a map of states that induces a square like this between the dynamics. And it's just saying what you imagine, so that the dynamics of a Moore machine is mapped compatibly with the dynamics into the cycle Moore machine. And of course, since these are lenses, we can compose this with lenses, with just composing lenses, and everything works fine. Similarly, we can define possibilistic or non-deterministic Moore machines, which are defined in the same way, and most importantly, over the same theory of composition. We're just changing which systems we're acting, like which systems, like there's a theory of system, we're just changing the systems, not the composition. We're changing them by adding the possibility of having multiple transitions out of a given state. And likewise, the maps are such that we need only, or like phi just needs to allow the transitions on the left to exist on the right, but on the right there could be more transitions. And this is all an example. These are all examples of free theories. So I said that theories of systems are algebras of pseudo-algebras of pseudo-monad. And like any good notion of algebra, they admit a free notion. And this free notion is induced by simply acting on displayed symmetric monadal category, which we consider like the generators of the theory. And we act on it with I, and what we get is a theory in which we denote with either notation, and a theory in which the systems are like over a given interface J are given by formal composite of a generator, which is in some fiber of this functor here, plus a process or a composition, formal composition in I out of this and into J, right? That's exactly what this diagram is expressing. And then the action is just given by composition for the composition part. And the most important example that is central in the book of David Jezes is that if we have a vibration like before, and we choose a section, then we can think the section is picking out for each state space of a Moore machine, for like potential Moore machine, like what are the possible like transitions out of that state. And then we can freely construct the theory of Moore machines by just saying that a Moore machine is given by indeed a choice of state space, which is given by this T, and like any Gödel length out of it, just as we've seen above, right? And notably, open ODEs are of this shape, where T is the tangent, bundle. The theorem of machine we just seen is of this form, where S is associated to the, like what we call S over S before, which is just like the constant bundle over S. And this is saying that if we're in a state, we can transition to any other state. But non-deterministic Moore machines are not free on the nose, but there's a way to construct them as a free theory. Sorry, well, you can construct free theory and then single out this theory as a subtheory. So it's sub-free in this sense. Okay. Let me point out also the behavioral theory and the related behavior theory associated to inadequate triple are also free. Basically everything we've seen is free, which is quite interesting. Okay, let's move on to Functorial behavior. So what is Functorial behavior is just the idea that behavior is a form of semantics for systems, right? So if you just tell me, if you just specify a few systems like Moore machines or open graphs, whatever you like, you didn't actually tell me how these systems behave, like what they do, what I'm looking into them, right? I might observe them, for example, just at the interfaces. I might observe what they do inside as well. I might observe them for a period of time. I might observe them for like infinite time. I might observe it for many, many different ways. And depending how I observe them, they have a different meaning, right? So that's very old adage in category theory, whereby we talk about some category of things in terms of how they map into another, specifically another of some form, and usually in our case it's a behavior theory, as you might have guessed, and usually this is set, right? But again, we might structure the behavior in many ways, so it doesn't need to be set. So behaviors are given by maps of systems theories. So what are these? So morphism of system theories is given by two parts. So the first part is the part dealing with the composition theories of the interfaces, and it's a symmetric lax monoidal lax double functor like this. And then on systems, we have a display symmetric monoidal functor like this. So the fact it's displayed means that it makes these commutes, so we can think of this sort of fiber-wise. And then there's all the structural morphisms that witness that we're not just functorial in the morphisms of systems and interfaces, we're also compatible with the compositional structure on systems. And the compositional structures comes in two forms. There's the monoidal part, and so we have the standard like lax monoidal comparisons, and then we have, let's say, the compositional structure with witnesses that we're compatible with composing the operations in this composition theories, and compatible with the composition of systems, right? So that if we look at a system with F and look at a composition with P, and then we put them together in the codomain, then we can compare them with what would happen if we had observed the composite directly, right? And of course, if the lax setters are invertible, then we say that this is a strong morphism, right? Strong monoidal, strong compositional, just strong. And so this is the general case for behavior is exactly the same, but we instantiate it for some behavior theory. So here it is for set, which is a sort of, again, exemplar case. And we see now, like, maybe the only thing to highlight here is that now indeed we are using, like we're mapping systems into something that we think of as sets of observations we have in the systems, and we compose them by composing the span. So like putting together compatible sets of observations and chaining in this sense some kind of like mutually compatible set of constraints that we have on some set of behaviors of observations. And a laxator like this is then saying, still works, is then saying that if we observe some systems and then we compose them like in some way, so by adding some constraints in a compatible way, so we are joining in these systems and not just considering them as two different separate things. And so we can consider this as sort of the behavior of the parts. Then we can compare then with the behavior of the whole, so the behavior of the composite, right? So this is a really interesting now interaction between the compositional and, let's say, categorical structures in the theory of systems, right? Because L is a morphism, so we need that, but it's talking about the algebraic structure, so we need the compositional bit. So just again on this part, I just want to highlight that if we land in a behavioral theory like SAT, which is a behavioral theory associated to a regular category, then the laxators, well, specifically L, can be factors an epimono as a surjective, a surjection and an injection. And we can think of these two parts of L as witnessing different obstructions to compositionality. So the first is like the one everyone thinks of, like everyone on the street even knows that the whole is more than the sum of its parts, right? And L0 is witnessing exactly this, is witnessing that the parts are missing some behaviors. So the behaviors, the parts are missing some behaviors of the whole. Okay, so there's some generative effect happening. But there's another kind of obstruction, which is less famous in my experience, which is that sometimes the part the whole may be forgetting some equations between, maybe adding some equations between the behaviors of the parts. The way to think about this is that when we assemble parts, there's like interfaces and points of context that are getting hidden by the composition operation, right? And so if we're not exposing them anymore, suddenly they get forgotten, and then there's behaviors of the whole that would differ by the observations they induce on the inner interfaces. And so the new equations are just witnessing that we are forgetting this. And so behaviors that used to be different are now the same. So there's also this part. But interestingly, it's quite common to ignore this bit by passing behavior through a functor that called black boxing that goes from basically from spans to relations. And it can be thought of as kind of localization. It's zero truncated things. And what it does, it like forgets the surjective part thing. It just forgets everything that happens inside systems and processes. And so we don't care anymore if there are new equations between the inner processes, because we don't talk about the inner processes. And so after passing through this functor, we only, we're just looking at the zero generative effects, right? So the possibly new behaviors introduced. And something interesting is that there's nothing that prohibits you from generalizing this to any other modality in the sense of like multi type theory, I guess. So for example, a Lex subcategory of, well, not SAT, but some other category of behaviors would induce its own like factorization of like obstructions of compositionality into different orthogonal directions. And I've yet to find like an interesting example of this thing, but there should be some interesting examples when behavior is like spatially or like geometrically structured in general, and we'll see later. So maybe there's something interesting there. So anyway, so this talk is about representable behavior. So it's about time. So what's the idea of representable behavior? Well, if behavior is sort of like a corporate sheaf, then why not representable corporate sheaths? They're the most obvious thing. There's two advantages of this, apart from like being extremely natural to consider. First of all, representable behavior is actually pretty common in nature, let's say, meaning that there's many interesting examples that you would consider even if you weren't interested in representable behavior. So I would even say that most behavior is actually representable in some sense. And then secondly, it gives you some kind of machinery to mend all the like structure that a behavior functor needs to have, right? Because as we're saying, it's not very complicated, but it's complicated enough that it's good to have some crank we can turn to produce behavior functors. So what is a representable theory of behavior? Well, it's one given by a system, like a choice of system C with interface H. You can think of C as a clock, or I will call it timepiece also, because literally a piece of time. So it's a nice pun and suggestive of something going on. But so it's a clock, so it has some kind of standard dynamics. Like a clock is a system with a standard dynamics that we use to measure other systems with, like we compare it to other systems. Let me do this. And then H, its interface are like the hands of the clock, right? So it's how we tell what's happening to the clock, right? If the clock didn't have any hands, we wouldn't be able to read the time. Very, very easy. So let's see how this functor, like the representable induced by a clock looks like. So on interfaces, so this is just a symmetric monoidal double functor out of I that's given by basically the representable H, okay? And so on objects and maps, so on interfaces and maps with interfaces, it's very easy to understand how this works, just the case of categories. On loose arrows, so the compositions, it's not very hard, but it's maybe a bit unusual, like maybe it's new to some people. So let's see how this works. So what we do is we map something like P to a span whose apex is the set of squares that, so the maps of compositions out of the identity of H and into P. So we map H as a unit loose arrow into P, and then any such square is going to have a top boundary, which can be conveniently projected here, and a bottom boundary that can be conveniently projected here. And if you give me now a square like this, then any square like this can be composed with theta to get a square like this on the other side. Everything commutes, and it's nice. And you can see that now when H is a comonoid, we can also define monoidal laxators in the usual way you do it on a comonoid. So by pairing and then composing it with the operation of the comonoid. But also the compositional laxators are pretty natural. So again, like if a loose arrow becomes a span like this, imagine if you had a composable arrow here, right? Then what you would do is just consider all the spans. So you would have another span here with all the squares mapping into Q. But now this, when we compose these two spans, we're considering all pairs of squares that can be composed. And then we can just compose them and get a square into the composite, okay? This is to say the compositional structure of I maps very nicely to the composition, like becomes the laxators of a representable. Much like representables in a category, okay? So also note that this means in general, these laxators are not going to be invertible, because if you have two squares, you can always factor them. We're going to see this later. Now on systems, we do something similar. So we take the representable out of C. So this is a category, so it makes sense to consider this. But now the representable out of C naturally lands in sets displayed over what? Over the observations we make of the interface of that system with H, right? So if you have S, then we get all the maps from C to S, but each of those maps is displayed over a map from H to I, where I is the interface of S and H is the interface of C, right? Because Cis is displayed over I. And then similarly, any map induces a square, and we're done. And now the monoidal laxator is induced in the same way of the local monoid structure of C, and the compositional laxator is also very much in the same way. If we have C here, sorry, if we have we have S here with a map out of C, and we have a map into P out of H, then we can get a map into C composed with P by simply acting with the operation in Cis, okay? So we're just like composing the behavior of S with the behavior of P. And again, this is in general not invertible. So let's see some examples. So the theory of trajectories in Moore machines, deterministic or not, is representable. So this is a Moore machine which has infinitely many states and just one possible transition between like consecutive numbers. It's exposing, so this picture means that this is also the output at this state. And then since this transition are labeled, it means that the input is always like one. There's no like trivial input. And now you can show, and this is done, for example, in David Jess's book, that if you map this into another Moore machine, what you get is a infinite trajectory in that other Moore machine, right? Similarly, if you want to consider fixed points of Moore machines, so states that like whose dynamics goes back to itself, you can map out of the walking fixed point, which is exactly like this dynamics embodied as a system. And the same happens for cycles of any order in this like family of walking loops of length, and represent this kind of behavior. Okay, this should be an example. States, so if you want to ignore everything the Moore machine does, just remember its state space. That's also something we can do by representing, by mapping out of the initial Moore machine, which simply is empty, there's no dynamics. And that states with observation can be obtained by mapping out of the system that has a state but has no dynamics. So that works in Moore P. Anyway, so how about compositionality? So let me summarize what we've seen so far about compositionality. So
Yeah. I was wondering if I could ask a question on your examples.
sure.
I was wondering, these make sense to me as like the systems, but is there a corresponding H for the interface? Does that make sense?
Yeah, sorry, I've been a bit fast and loose. So
No worries
something
at all.
like
I
this,
just wanted
something like this is given by the natural. I don't know what's happening to my pen. So the interface here is and, so again, the output is given by this, and the input is trivial. So at any moment, there's only one possible transition. The walking loops are similarly defined, so they broadcast their state, and they receive no input, just like a trivial input. This is the empty transition, the empty interface. So there's already empty system over it. And this is also L0 is something that's like its interface is better. Oh God. You can think of it as a polynomial functor, so it's like 1, 1, 0. I think as a polynomial functor, this is just 1, right? It has some output, but no inputs to come in.
Uh-huh.
So the transition
Thank you so much. I really appreciate it.
Thanks, Sophie. Okay. So depending on properties of I and cis, we can get some properties of the representable behaviors in them. So for example, very easily, if I and cis are Cartesian monoidal, then mapping into a product is exactly the same as mapping into each factor separately. And this means that the monoidal laxators of these representables are always invertible. Conveniently enough, that's the case in all the examples we've seen. Similarly, when I is span-like, which means, well, I'm just going to do it the easy way. So span-like means, again, that these laxators are invertible, so that mapping out of an identity into a composite is the same thing as mapping into the composite, sorry, into each factor separately. Again, in this case, the laxators are invertible, and again, this is the case for all the composition theories we mentioned so far, because we constructed them as theories of spans, right? And spans are span-like. And you can see why span is span-like, because we're mapping into a pullback. So mapping into a pullback is the same as mapping in the two factors. And finally, I say the theory system is observable when mapping a system into a composite is the same thing as mapping into the system and into the composition separately and then put them together, which again can be seen as saying that the compositional laxators are invertible, right? So we can always sort of factor the map into a composite into two different maps, right? And now, unlike the other two things, this is not a very common thing to do, as you might have suspected. But note that there's no need for these properties to hold for the entirety of a theory or systems or composition. It's enough they all add an object, meaning that for that specific representable, those specific laxators are invertible. In which case we say that that system is Cartesian or span-like or observable. Okay, and so now we'll devote the rest of the talk to tell you how to get observability of a system. So Cartesian span-like, again, pretty common, not really hard to get. Getting the third is the interesting thing. So let's position ourselves in a theory associated to an adequate triple. So it's a kind of behavior theory. It's constructed like a behavior theory. Let's observe this. So this is one of those factorization problems that are associated to observability, right? So we have a system here, which is just a display map, and we're mapping it into a system composed with some composition, which is in this case a span, right? And we have a map into this, and we want to factor it as a map between the systems composed with a map between, like, from this identity to this thing. And I claim this is equivalent, in fact, this lifting problem here, okay? And the way to see this is by drawing more arrows. So if we have something like delta, then we can show it there and then compose it with P sharp, and we get this. And on top, we can just resort to alpha. There's no problems, which, like, in this case is actually trivial. And one can see, like, it works both ways, and that delta is exactly like this. Two commutativity conditions correspond to the commutativity conditions we have here. And so that's quite interesting. And also, we never use the fact that this boundary is trivial, right? So we have a very general lemma, in fact, about factorizing squares in a theory associated to an adequate triple. And so the fact that the boundary here can be whatever you want means that we can take a free theory over the spans, over the theory of spans associated to an adequate triple, and we get a compositionality theorem out of it. So just to go slowly through this, if E is a symmetric monoidal adequate triple, and then we have some displaced symmetric monoidal category of generators, Then the free theory is a theory on span E, whose systems look like this, right? They look like span, aggressive spans, with the top boundary being given by something in the form TC for a generator C in X, okay? Now, this system is observable, meaning that those laxators were invertible, if and only if this map C, which we can think of as the observation map, right? That's actually outputting something, as this lifting property with respect to aggressive maps, right? So it lifts, again, all aggressive maps uniquely.
Matteo, just
Sure.
be sure you got an eye on the time. Hopefully you can get through this in like less than 5 more minutes-ish.
Yeah, I'll finish this and then.
Awesome.
So this theorem specializes to like one direction of this theorem specializes to a theorem of David Jazz's and from his book, where he talks about Moore machines, and we've seen the Moore machines are like something of this form, with P is a vibration, T is a section, then PT Moore machines are indeed something like this, which is a special case of this. And now we conclude that this is observable, as in it induces a strong compositional representable behavior, if and only if C is invertible, because this lifting problem is just equivalent to say C has the left lifting property, but it's left orthogonal to all maps, and that's what invertible means. And then as an interesting corollary to this, we also get it if C is just split epi, which means we can observe the system, right? But many outputs can correspond to, one output can correspond to many internal states. In this case, we still get no zero generative effects, right? So we still get no behavior, no whole has more behaviors than the parts, right? We only get that the whole has more equations on behaviors than the parts. So I'll wrap up quickly. So what I wanted to say here is that, well, you can do more. You can represent behavior by families or even diagrams. And there's some interesting things like, well, for example, if you're interested in more machines, you're not always interested in just infinite trajectories. You might be interested in finite trajectories. For example, to automata, like accepting words is there is a finite trajectory with that kind of input. And you can get some insight in the compositionality of this behaviors. I'll just go to the end though, which is that in general, so something interesting to consider is this. You have a theory of systems and you want to consider like a diagram of systems in SIS, which you consider to be like the walking trajectories of some kind. So not just one clock, but there's many clocks of different lengths, of different like type. And then you can plurirepresent this, like use this to get a plurirepresentable functor, but it's more interesting to do a nerve construction. So to consider what happens when you map out of SIS into T variable sets, right? And that's really nice. And set T op has many monoidal structures, specifically has Cartesian products, and that gives you some kind of compositionality with respect to that monoidal product, or it has the convolution with respect to the product you have in T, which is a bit nicer. And now if C, so your diagram is strong monoidal, then so is the nerve. And then you get a compositionality theorem, which goes like this, that this nerve behavior, so this functor here, is strong monoidal and strong compositional as soon as your diagram of timepieces is strong monoidal, and each timepiece is observable, meaning it's representable, is strongly compositional. All of its interfaces are span-like, meaning it's representable, is strongly compositional. And so you can reduce the problem of representing like a very varied notion of behavior into just the problem of, well, I mean, of representing that strongly compositionally into just representing each behavior strongly compositionally, for which we just seen a quite general theorem. And that's pretty much it. There are some directions here, but I won't bother you any longer. Thank you very much for your patience and attention.
Great. Thanks very much, Matteo. We'll have you back next week for the other half, I'm sure. Very nice. We now have just a little bit of time for questions while the stream is going, but if we have more questions than time allows, maybe we can go off stream and keep chatting a little bit longer. So if you have a question or comment for Matteo, you can feel free to raise your virtual hand or drop it in the chat and I can deliver it. Any questions? We're all just taking a deep breath after all those definitions. I see Gabriel has a question. If you'd like to unmute and go ahead, Gabriel.
Yeah, hey. Okay, so first of all, thanks so much. This was an incredibly interesting talk. I just wanted to know if you considered, I was really interested in this last part about like nerves as generalized behaviors. And I guess it's obvious, I don't know, question would be when you have a nerve, you have a realization functor if you have the co-limits. So there you take just the co-limit of the nerve to land in set, but you could also say, oh, what if I want to represent this by another system and like taking some sort of realization functor? Would that be interesting in this context?
I think it would be very interesting. I also thought about that. So at the level of like displayed categories, so the type data, it works in many interesting examples. Because often like your systems are like rich enough to be co-complete. I didn't think of the interaction with the compositional structure yet, which is one of the problems of the open problems right now, and something I need to work on more, which is like you have to sort of carry around the structure by hand all the time. And it would be much nicer if you had some sort of like formal category theory worked out for the setting, such that you can talk about like the classical theorems of category theory, like Yoneda and taking co-limits, like things like that. Just do it directly with all the algebraic structure carrying over. So at the moment, I cannot tell you like, yes, there is a realization functor in like, for example, more machines, and that works and it's amazing. It works. I don't know if it super works.
I see. Thank you. That sounds really interesting. Would love to see more of that.
Yeah.
Sophie asked, why did you call it observable systems?
Yeah, thanks for the question, Sophie, because I wanted to say more about that, but I didn't manage my time well enough. But anyway, so the idea is that an observable system, where are you? Here, okay. So an observable system, so at first it seems as something like that it can observe other systems. Actually, it's witnessing the fact it can observe it, right? Because this is saying like you are sort of simulating C inside this composite, right? And now this is saying that if you do that, it's the same thing as simulating C inside S and also getting what's happening in I, right? So the really like meaty bit of this property here is that we can do this thing, right? That we can find this map. And finding this map means that the observability of C is such that when you map it into another system, you can still see its dynamics there and use the fact that C is observable to understand what's happening in the other system, to the point that you can say what's happening in this inner interface, right? So that's my intuition for it. Mathematically, it's witnessed by the fact, at least for like this class of systems, well, that you have this lifting property, right? This saying if you can map, like, let's say the state spaces or some kind of internal state of your system to this other system here you have on the right, and you can map also the observations you make at the interface, then you can actually lift the observation you can make at the interface to reconstruct what happened inside the systems you're mapping in, right? So it's saying that the clock is observable because it can be used to reconstruct all other systems around it, in a sense. If it weren't observable, it couldn't observe other systems through it. And that's why it's observable. That's my intuition.
Thanks. That helps. Thanks.
Thanks.
Valeria's got a hand, and I think that'll be our last.
Hi, Matteo. Thanks very much. It was a great talk. I kind of understood a few bits more of this stuff. I particularly liked the beginning when you talked about double categorical systems, where double categorical systems comes from. And so the question is a little bit vague, but it is as follows. The other places where we get double categorical structure from, when you're thinking about programming languages, the fact that you want terms to reduce to other terms and you want to track this reduction. Is that happening here at all?
So
or is it a completely different intuition?
No, I think that's an interesting observation. I've been toying with this idea that, PDL, right? Propositional dynamic logic. And it's this logic you build out of basically a toy syntax for a programming language, but this toy syntax can be like serious syntax if you like. And the idea is that you build your programs inductively out of little pieces, and then you can like interact with the logic. But now if you throw away the logic, you just have this idea of inductively defined programs. That's actually a very similar idea. I mean, when you freely generate a theory here, what you're doing is the same. You have some bits, and then you're freely adding all possible composites. So what you can do, and it's something I've done, is you take a syntax for a programming language, and you can represent it as a double category. If you have a notion of rewriting for terms, of reduction for terms, then the two cells are actually non-trivial. But otherwise, you just have a trivial, like a discrete, in that direction, a tightly discrete double category, in which your loose arrows, your compositions are just this piece of syntax. And then that's it. You just have this double category. And I think the interesting thing is that when you look at what I call the theories of behavior, so this double, functors out of this double categories. So you add a theorem system on top freely, and that's not very important. But when you map into set, what you get are the notion of Kripke model that you would expect, right? So a theory of behavior on a programming language in this sense is exactly a model for that programming language, which I think is really interesting, especially when you consider building now sort of like the home theory of systems, right? So you consider all possible behaviors, and now you have theory of systems, the theory of models of that programming language. So I think there is a connection, but so something that I don't know how to do is how to handle all the extra structure that programming languages have, right? Just
Right.
not like just have parallel composition and sequential composition. You have much more. So that's extra structure on top of your theories.
Yeah, I think even in the restricted thing, there's stuff to be proved, right? We don't, I mean, I have no idea what this subclasses of systems that you're talking about is spun like. I mean, Cartesian, okay, it's obvious that you need to have products, but and especially observable, what that would mean in this case is not, at least to me, not clear. But thank you very much. That was very interesting.
Thank you.
Great. I will now end the live stream. Thanks again, Matteo. If there's any other, if you don't have to run